Whether it's a chatbot writing code or a model generating a photorealistic image, the underlying intelligence is driven by a single mathematical mechanism. Consider the sentence, "The animal didn't cross the street because it was too tired." To understand the thought, you have to know what the word "it" refers to. A human identifies the animal instantly, but for decades, this kind of contextual link was an engineering hurdle for machines. Early models, called recurrent neural networks, processed language in a strict sequence. They analyzed one word at a time, creating a fixed-size summary and passing it forward like a message in a game of telephone. This sequential approach created a bottleneck. Because the summary container never changed size, whether the sentence was 5 words or 500, the information from the first word begins to decay by the time the model reaches the end. This decay meant the model effectively lost the beginning of its own thought process. Without the ability to look back at earlier words, AI was limited to processing short, simple phrases, unable to track the complex relationships that give human language its depth. The breakthrough came in 2017, when researchers proposed moving away from the linear telephone line entirely. Instead of passing messages forward one by one in a slow sequence, they designed a totally new system that allowed for massive parallel processing. This new architecture functions more like a group chat. Every word in a sequence has direct access to every other word simultaneously, removing the need for a sequential summary. Because the model sees the entire sentence at once, no information is lost through a chain of handoffs. The system has uncorrupted access to the full context of the text it is reading. If every word is looking at every other word at once, the system needs a way to filter that data. It has to mathematically determine which specific connections are actually relevant to the meaning of the sentence. First, it sends a query vector, asking, "Where is my reference?" Simultaneously, animal broadcasts a key vector. The model compares them, calculating a high score for the match. Finally, a value vector sends its payload, letting it absorb the meaning of animal. Through these three operations, a blank pronoun is rewritten as a blend of its neighbors. Meaning is no longer found in a static dictionary, but in the mathematical relationships between words. Identifying a pronoun's reference is only one part of a sentence's structure. Language contains multiple layers of meaning happening at once. In our example, the word "it" doesn't just need to connect to animal to identify the subject. It also needs to connect to the word tired to capture the state of that subject. The solution is multi-head attention. The model runs several of these search operations in parallel, with different heads specializing in different types of relationships, one for grammar, one for syntax, and one for nearby context. This parallel processing allows the model to map the entire architecture of human language simply by reading millions of texts, discovering patterns like grammar and co-reference without ever being taught a formal rulebook. Because attention is a mathematical way of comparing pairs of elements in a sequence, its utility extends far beyond text. Vision transformers treat patches of an image like words in a sentence. By using attention, the model learns that one patch containing an eye is highly relevant to the patch containing the other eye, helping the machine understand the structure of a face. In biology, AlphaFold uses this mechanism to predict how proteins fold. It calculates how amino acids that are far apart in a sequence will interact once they are folded together into a 3D structure. This core mechanism provided the foundation for scaling from a 2017 research paper to the multi-billion parameter architectures behind GPT-4 and Claude. Modern AI relies on this mathematical application of selective focus. By rewriting every piece of data as a blend of its neighbors, the mechanism allows machines to derive meaning from the relationship between parts, providing a bridge between raw data and true comprehension.